So today our idea is to find intersections of things where lines and planes intersect, where planes and planes intersect, and two lines intersect, if that can happen. I suppose that can happen in 3D, right? And then we're going to be looking for distances. Now, we're going to be looking for like a distance between two planes or a distance between a line and a plane, provided that they don't intersect, right? But to really to find those distances, you really just need a point from a line or a point from a plane. And then if you can find a distance between a point in a plane and a point in a line, then I think that would be good. Our distance formulas will end up becoming formulas. But if you ever forget the formulas, we're going to go through a process of projection to find those distances. So I don't know if anybody asks what's projection used for. Here's another use for projection of one vector onto another vector. All right, let's take a look at intersections. Well, let's take a look at the structures first of these lines and planes. So let's do a little quick recap. So a line, and I'll write this in the most convenient form. I'll write whatever we're talking about in convenient forms. But I'm going to expect you to be able to go from a vector form to a parametric form to a symmetric form and vice versa. Because sometimes in the problems that they give you something in symmetric form and you have to write it into vector form or something. So here I'm going to write this in vector form, kind of. So we have a point times t times a direction vector. And I'll put an arrow around the point on top of the point to say it's in standard position, a vector in standard position. But it's really just the point. So I think for me, this is the most workable form of a line. And then you can always adjust it to a parametric or a symmetric form if you need to. And then a plane is most often written in scalar form with x, y, z. And then we have the constant d, which was found by taking the dot product of the normal and some random point on the plane. Now, we should also know that ABC is the normal vector for this plane. So if we ever need that vector, then we're going to be able to use it. Okay, so these are the basic forms, and what we're going to do is we're going to find intersections and things like that. All right, so if I give you an equation of a line, if I give you an equation of a plane, there's two possible things that can happen. One, they'll intersect, or two, they won't intersect. So let's examine a line and a plane. So a case where they don't intersect means that essentially that line is parallel to the plane. I don't know if parallel is the best word for this, but it means it won't touch the plane. How can you show that a plane and a line don't intersect? What has to be true for a plane and a line to not intersect? Yeah?
They don't lie on them, but the plane's not.
Probably. John?
You take the cross product and you found an orthogonal vector. So one of them, you should be able to take the dot product with that orthogonal vector and both and be equal to 0.
Okay.
It's kind of extended, I don't know.
That's a general idea. You're a step into the direction, a hop into the direction, you missed a step. Or you don't need a step. I don't know. Does anybody take his idea and kind of solidify it for this example? No? And the other thing is that part of the missing explanation that John was saying was that there's a vector involved. I don't see any vectors here yet, so we need to elaborate on which vectors. And there's a cross product that could be important in this case, but given our information, and by that I mean given the equation of a line and a plane, I'll say that in that particular instance we don't need the cross product anymore. So, what do we need to do? Okay, let me see if I can lead you to some steps. We know that for the plane we have a normal vector. That normal vector can be pulled out of the equation, right? The coefficients of x, y, and z. So we know that there's a vector that's perpendicular to the plane. We also know that this line, whether it's written in parametric form or symmetric equations or in vector form, that there is going to be a direction vector that we can somehow pull out. Now what do we do? Yeah, so if you take the dot of these two things, they should equal to 0 because they should be perpendicular to each other. That's what you guys meant to say. Oops. Right. Or if you're not given it directly, you can somehow take it, find it. So these two vectors should be perpendicular to each other. Okay? And if you take the dot product, they're not equal to 0. That means this line is somehow tilted. And if the line is somehow tilted, then eventually it'll intersect the plane somewhere. Okay? So that would be case 2. So case 2, if you take the dot product of the appropriate vectors and you don't get 0, that means they're not perpendicular, which means that line will eventually hit the point or hit the plane somewhere. Is it possible for this line to hit the plane at more than one point? Say intersect at exactly one point. And we should be able to find it. Okay? So let's do an example. We can make it up, or I got this set up so that I have the class examples, not the homework anymore. But now I have to find a problem. That's the other thing I need to do, is find problems before class. Equation of plane, point. All right, let's do number 29 here. So they say it's going to intersect, but we'll take it another step and say, take a step before to say that these two things will in fact intersect, that they're not parallel. Find the point in which the line intersects a given plane. So here our line is given in parametric form. So let's first show, I know it's not in this problem, but let's take an extra step and show that the line and plane they actually do intersect. So what we're going to do is we're going to find the equation, or not the equation, but the direction vector of the line. Can anybody find that real quick? Or should we go through a little bit of the work? Let's go through a little bit of the work, and then from here on out you should be able to find this direction of the line. What we're going to do is we're going to write it into one vector with each of these components, 1 plus 3t, 4t, and 5 minus 3t. And then we're going to kind of separate these things into pieces. I'm going to find all the coefficients of t and then factor that out. I'm going to find all the numbers that don't have a coefficient of t and then separate it as its own vector. So this is actually the point that this particular line starts with. And then after I take that out, what's left is a 3t, 4t, and a negative 3t. But all those have a coefficient of t in it that we can take out. And then we have 3, 4, negative 3. So this, the 3, 4, negative 3 is a vector that we're looking for that gives the direction of the plane, of the line. Now let's take a look at the plane. I think that's easy enough to find the normal. So if we just write this down, x plus 2y minus z is equal to, or plus 4 is equal to 0. You can just say the normal vector is 1, 2, negative 1. So given that piece of information, we could just take the dot product of 3, 4, negative 3 with 1, 2, negative 1. And it's going to be whatever it is, but I don't think it's going to be 0. And I suppose you could double check that, but I'm pretty sure it's not equal to 0. What's the dot product equal to here? What? 14. Okay, but the point that it's not equal to 0 is what we really want to get at for this particular problem. So we know that these will eventually intersect, which is what they are saying here. So we're going to find the intersection. Okay? Questions so far? All right, so they will, yeah. The 1, 0, and 5 would be like the 1, 0 plus 4t and then the 5. These are the terms inside of that don't have a t. And then the terms with a t, I'll keep it over here so I can factor the t out. Okay? Yeah. 14 is the dot product between those two vectors, the vector for the direction of the line and the vector, the normal to the plane. Okay. And what we want to get is whether it's 0 or not 0. And at this point, whatever it is doesn't matter.
If it's 0, it doesn't.
If it's 0, then it doesn't intersect, correct. Okay? All right, so now that we know that it intersects, aside from them telling us that it intersects, what we're going to do is when you find intersections of things in your, back in like algebra, what did you used to do when somebody, instructions and the thing tells you to find the intersection of something? Set them equal to each other, right? So in this case, I think it might be a little bit more obvious. It's less obvious if it's in different forms. But in this case, I think it's a little bit obvious what you need to do when you say, quote, set them equal to each other. Any ideas? Yeah? What thing? Help me out, Matt. What thing?
I don't know what it is.
Close. Yeah. So we have, I don't know if that's what you mean, William, but we have the, or Matt, is it, you have the x is equal to 1 plus 3t, and there is an x slot over here. So we would take this 1 plus 3t and put it in for x. And we're going to do that for y and for z. And then what we'll have is we'll have a function of t. Only one variable, which is even nice. It's a linear equation. We can easily solve for that. Okay, so this is what's going to happen. What you're going to do is you're going to take your line equation, and I'm going to save some spots for the variables. So we're going to take our line equation, which is 1 plus 3t in the x, and so we'll replace the x value for that. And then the y, 2 times y is equal to 4t. We'll replace the y with that. And then the z minus z here is 5 minus 3t. And then we have that plus 4, that constant, so we'll just leave it there. But now what we have here is a function of t, or not a function, but it's an equation of one variable t, and so we can just solve for that. So let's do the distributing that we need to do. 1 plus 3t plus 8t minus 5 plus 3t plus 4 equal to 0. Let's take all the constants and bring it to one side. So they all go with a negative. That's 0, right? Wow. I guess it doesn't matter what this is, but if we actually find out, 9, 17? 14? Are you sure? Yeah, you're probably right. So t is equal to 0. Yeah. Yes. So the t equals 0 tells us, if we were looking at this as a time, the t is equal to 0 is the time when the line hits the plane. And like Matt said, we take that t is equal to 0 and we put it back into the parametric equations for the line, because that's the only one that has a t in it, right? The plane doesn't have any t's in it. So we'll put it back into the line equation. So t equal to 0 for the line. You get x is equal to 1, y is equal to 0, and z is equal to 5. So in this particular case, it just turned out to be that starting point, because that's the point when t is equal to 0. And we want to look at this as a point. Notice that their answer wants you to treat this with a parentheses. That would be 1, 0, 5. Yes.
So if you did the work and you had, could you then just plug T in over there, and that would still fix that, or is there a case where, like, do you always have to plug it back into that equation?
Yeah, you need
Which equation?
you need to plug it back into the line equation.
Okay.
And I guess my line was in green, so I got messed up with the colors here. But I could just change it into green. Okay. So that's the intersection between a line and a plane. All right. That was an easy one. Now let's take a look at the intersection between two planes. So if you had a couple of planes and you threw them up in the air, there's only two possible ways. It's like if you have two sticks and you put it on the floor, you drop it on the floor. There's three things that can happen, right? They could be right on top of each other. Well, that's hard to happen, but it could. And then they could intersect at exactly one point, or they could be parallel and intersect nowhere. Remember that little thing that you did in algebra? It's two equations, two unknowns, and two lines kind of business. And you get a system of linear equations. So now we're in higher dimensions, so we're imagining what might happen to two planes. So the two planes can either be exactly the same plane. If you throw these two planes in the air and then they land on each other in space, they could be exactly the same plane. So that's kind of boring. But the other two cases are, they could either be parallel, parallel planes, so what has to happen if the two planes are parallel? What can you say about, there are some of the interesting aspects of their equations? Normal vectors should be don't have to be exactly the same, but same direction, scalar multiple of each other, parallel. Okay, so the two normal vectors should be parallel to each other. So it's quite possible that one vector would be going one way and then the other vector would be going the totally opposite way. But as long as the two vectors are parallel, then the planes themselves are parallel. And then case two, they intersect. How would they intersect? Yeah. They would intersect in a line. If you look at your laptop or a book, open the book a little bit, pretend one side of the book is one plane and the other side of the book is the other plane. They intersect at the binding, kind of like your laptop. They intersect at the hinge. And what is that hinge or whatever? That's the line of intersection. So it's possible. Oh, I haven't drawn this in a while. But they intersect in the line. Okay. So it's easy to check if they're parallel, if the two vectors are parallel. You can take the cross product. If the cross product is equal to 0, remember there's a sign in there between. So if the sine of 0 or sine of 180 degrees is 0, so the cross product, if the cross product is equal to 0, then they're parallel. And so I'd be more interested in finding the equation of a line of intersection between two planes. So intersect in a line, that's what that says. Some of you guys are squinting like instead of raising your hand and asking, what does that say? Intersect in a line. You guys used to my handwriting yet? All right. Yeah, I know you're lying, but it's all good. All right, let's take a look at, see if we can find an example. Find the point at which line intersects a plane. Find the direction numbers of the line of intersection. Let's do number let's do number 34. Let's see. So I'm going to copy this, and then I'm going to go back to our previous page and talk about one more thing that they're talking about here. Here, determine whether the planes are parallel, perpendicular, or neither. So I talked about parallel. I didn't talk about perpendicular, but perpendicular is just a measurement of an angle. And so what you want to do is, I'm going to go back over here to this picture. The two planes intersect. If the two planes intersect, they would intersect in a line. Now, they're normal vectors. The planes have normal vectors, remember. And I'm just going to draw a couple of normal vectors in this drawing over here. Maybe one that looks like this. That's perpendicular to that. And then the other one is, I'll say it's coming out this way. And these normal vectors to the planes are useful for in a couple of ways. One way that it's useful for is that if you take those two vectors you'll find a couple of things here. One, the angle between these two vectors, I guess I drew it in a way where it actually, the angle over here is a smaller angle. That's too difficult to see. Anyways, the angle between those two vectors are exactly the same. The angle is exactly the same as the angle between the two planes. Think about that. If you have that laptop open a little bit or a lot, or the book open a little bit, or a binder, and then imagine the normal vectors that are perpendicular to those planes, the angles between them is exactly the same as the angle between the planes. Yeah? I'll take your reluctant nods or confused face as being okay. Unless you can ask a question. Can you picture it? Okay. So, you can find an angle between the planes, and so you could tell if two planes are going to be perpendicular to each other by just looking at their normal vectors, because those normal vectors will be perpendicular to each other as well. But there's another use for these normal vectors. Yeah. Mm-hmm. Yep. And if you take the cross product, remember that the cross product gives you a vector that's perpendicular to both of those vectors. If it's perpendicular to both of those vectors, that means it's going to be those vectors. You're going to find the direction of the line of intersection. So the cross product will give you the direction of the line of intersection. It'll be a direction vector for your line. Okay? So that's one of the two things that we're going to need for an equation of a line when we find the equation of the line of intersection. But we're going to need one more, and that's going to be a little trickier, but we'll talk about that when we get there. All right? So let's go back to this problem and see if we can address its issues. And if they do intersect, if they're not parallel and they do intersect, then we're going to take this a step further and find the equation of the line of intersection. So we have a couple of planes. We have 6x plus 24y minus 18z is equal to 1. That's one plane. And then the other plane has negative 3x plus 6y plus 7z is equal to 0. So those are our two planes. Let's extract the normal vector from each of these planes. So let's call this plane 1, and so n1, the normal vector for the first plane, is going to be a 6, 24, and negative 18. They look like they're all divisible by 3. If you want, you can factor out a 3 to make your computations a little bit easier, or you can just leave it like this. It's up to you. The other vector, the other plane, we'll call plane 2. We'll have a normal vector n2, and that's negative 3, 6, and 7. Now, if you can somehow set them equal to each other, this is one way, instead of doing the cross product, this might be a quicker way to check to see if they're parallel. You could say 6 and negative 3, if I multiply this by negative 2, I'm going to get 6. So I would need to multiply everything by negative 2, and if I get them to match up with the other vector, then I could say that they're collinear, they're parallel. They're scalar multiples of each other. And of course, the other way to check is the longer way is to do a cross product. Okay, yes? I was going to use the cross product to check if they're parallel to each other. But if I just want to check if they're parallel to each other, I can set n1 equal to some constant times n2, and if I can find that constant, these things are vectors, and if I can find that constant where that would make this a true statement, then I can say that they're collinear to each other. They're collinear, they're parallel, they're scalar multiples of each other, and so I would be done. So the question is, can you find a k so that this is true? I think the k would have been like a negative 2, like we said over here, but negative 2 times 6 doesn't equal to 24, so I think we could be done there. So in this case, no such k. Suck. sometimes when I write secant x really quickly. No such k, so we can conclude that this is not parallel. Okay? So we could check if they're perpendicular by taking the dot product of the two normal vectors. And if you get them to equal to 0, then you can say the two planes are perpendicular. Again, you could have factored out that 3 from the first vector just to have slightly smaller numbers, and I didn't do that, so I'm going to have big numbers. Well, actually, why don't you just tell me what I get? I guess I do want to compare. Is it 0 or not?
Yeah, I'm looking at 0. -48 plus 144. No, -18 plus 144 minus 1.6.
So that's 0? Can we get a confirmation on that? Yeah? Okay, so it's equal to 0. And so we could say it's perpendicular. All right, in this particular problem, that's all they ask for, and then we move on. But let's actually find, so they're perpendicular, they still intersect, so we should still be able to find the line of intersection. So let's take this and say we're going to find the line of intersection. Okay, so remember the approach for finding the line of intersection. We need a line, so I'm going to underline the word line here and say we need two things for the line. We need a point and a direction vector. So the direction, I think we can find the direction vector by just crossing the two normal vectors, right? So N1 cross N2. I guess we should have done this earlier, so we would have gotten the answer. But let's take the cross product. And the direction of this line, whether it's going one way or another way, it doesn't really matter. So it doesn't matter which way you cross this. Remember, cross is anti-commutative. But it would still be the direction idea. All right, let's see. Imagine N1 on top, N2 in the bottom, 24, 7. I'm not going to do this. Can you just... All right, seems like we got a result here. Big numbers.
You could have just taken a cross product at the beginning, and if it was 0, then you know you're
Yeah. We could have done that. Should have done that. Either case, I probably would have used Wolfram alpha anyways.
Is the sign of the angle similar to the cosine cosine is A dot B over the magnitude, over the product of the magnitude.
Yeah.
So sine theta is A cross B over the product of the magnitude.
Yeah, except the cross product is a vector, so you want to take the magnitude of that vector. So it's a magnitude of A cross B
Oh, right.
divided by. Yep. All right. So we have a direction. Now the other thing we need is a point. What? How are we going to do this? All right. Well, let's take a look at my awesome drawing here. We want to find a point on this line somewhere, anywhere, right? And so I think we can find a point on one plane and find another point in another plane, but there's not a very likely chance that they would be the same point. So that might be a little difficult. So what we're going to do is we're going to imagine this line will eventually hit a plane that we might be familiar with, like one of the coordinate planes. Give me an equation for one of the coordinate planes. Do you know what I mean by coordinate plane? Say it again? No? Close. XY plane. What's the equation for the XY plane? Z is equal to 0. William, so we're just looking at one variable equal to 0. And I could set any variable equal to 0, and that would imagine, if you can imagine, that would be one of the coordinate planes, either the XY plane, the YZ plane, or the ZX plane.
It would be the plane made by the two axes.
That's not, yeah. So that's what we're going to do. Oh, I'm back to this picture. I'm going to imagine that this point or this line will eventually hit one of the coordinate planes by setting x equal to 0 or y equal to 0 or z is equal to 0. In fact, you could set it equal to any number you want. Just 0 seems to be a nice number because that might simplify our calculations a little bit. So that's what we'll do. We're going to set z equal to 0, and geometrically what this is looking for is where this line, where the line that we're looking for will intersect the xy plane. And you're not restricted to just having it intersect the xy plane. You can have it intersect the yz plane or the xz plane. Or you can even have it intersect another plane, like z is equal to 2, if you want. Right? But what does that do? How does that make our job a little bit easier? What we're going to do is we're going to take our two equations of the line. We got 6x plus 24y minus 18z. And for z, I'm just going to leave this as a space right now, equal to 1. Because now I'm going to get to put that constant 0 in there. And the other equation looks like it's negative 3x plus 6y plus 7z. Again, I'll leave that open because I'm just going to drop a 0 there. Because we set z equal to 0, so we could just put 0 in for z. So 0 in for z, we have two equations and two unknowns. 6x plus 24y is equal to 1 minus 3x plus 6y is equal to 0. We've established that this plane or this line will hit the xy plane. That's when z is equal to 0. So all we're left to do is find the x and the y components. of where these things are going to intersect. Damn, it's 150 already. All right, let's finish this. I would multiply the bottom by 2. I'm going to use one of those methods. I forgot which one. Yeah, sure, I think. So multiply the bottom by 2. I'm going to get 0 for x. 24 plus 12 is 36. Y is equal to 1. Y is equal to 1 over 36. And x is going to be, well, I need to do a little bit more work on that. 6x plus 24 over 36 is equal to, oh, I want to do the bottom one. Sorry. Seems a little bit easier. The bottom one is negative 3x plus 6 times y is equal to 0. It's easier because it's 0 on the other side. Negative 3x, 1 over 6. So put the 1 over 6 on the other side and divide by negative 3. That makes it into positive. 3 times 6 is 18. I think this is good. And so finally, I have my point. My point is 1 over 18, 1 over 36, and 0. And so the equation of line I usually call it L of t in vector form, would need a point, 1 over 18, 1 over 36, and 0, plus t times the direction, and the direction we found from the cross product, 276, 12, 108. You see this is not a very nice looking problem. The numbers are huge and fractiony. But that's how you would find the equation of the line. Okay? Yeah?
If you want to, instead of just doing the cross product thing, you can just do the second half of it, but do it twice with 2 different planes, and be 2 points.
I don't know if it's going to be the same direction as the line, though. Will it? Let me think about that. All right, it's time. So we're still not quite done with this. So I thought we were ahead, and then now today we were caught up, and now tomorrow we're going to be a little bit behind. Well, we'll see how it goes. See you guys tomorrow.